Welcome everyone to our Routing Switching Essentials meeting for this week. I want to very quickly go ahead and state that I apologize. I want you to know that I am very much sorry that I don't have more of the assignments in our class. Most of you have been doing the packet tracers and the labs. I'm working on those labs. We're trying to map them into the NetLabs. The NetLabs version 6 labs are not released, and so we've had kind of a problem there. I will tell you this too. I want you to be aware, I know our class ends in 2 weeks officially, but I'm going to leave NetAcad open so you can still continue to work in NetAcad. So don't have a heart attack as we are, I know, behind in terms of my going through the chapters. Hopefully you've been reading ahead. I always tell my students when I say read chapter 1, and then when you're done with chapter 1, read chapter 2, and then when you're done with chapter 2, you read chapter 3, and so on and so forth. So just be aware of that. I want you to know that we will have some time, and you will be able to continue a little bit past when the class officially ends. All right, so let's talk about switch networks. We've talked a lot about routing. We've been talking a great deal about routing, but this is the routing and switching essentials course. So we need to talk about switching. Switches are, for the purposes of CCNA, for the most part, layer 2 devices. So they're data link layer devices that filter based upon MAC addresses. Here we have some of the different reasons of why networks are more complex. One of the big things is that we have converged networks. We now have unified communications. We have voice over IP. We have IP surveillance cameras. We have everybody and their brother with a phone that can do 50,000 things. Jason, am I having a problem with the audio? Can y'all hear me? Drop in the chat if it's not working. It's fine on Sabir's in. Kurt, you're good, so you're okay. All right. If there is a problem, Jason, let me know, and I'll try to fix it on my end. But I think things are. Here we have our converged networks. So we've got voice, video, and data all on the network. Now, it's funny because I just filled in for someone in a Network Plus class, and the okay, yeah, Jason, drop out and come back in. I'd probably fix it for you. I just filled in a Network Plus class, and the funny thing was that the chat was on converged networking. And I always talk about how convergence is a wonderful thing and a horrible thing. It's wonderful in that it allows you to do away with that dual network. You don't have to have a phone network and also a data network. However, it means that your data network is now extremely important because when I pick up my phone, I expect to hear a dial tone. We, in the world that we've grown up in, we expected 5 volts DC to be on the line to run my phone. So when the power goes out, I expect my phone to work. If it doesn't, then there's a problem. And there's all types of problems, from everything from how do I call 911 and the power failure to the fact that I have to go in and do UPSs for my switches because my switches now control my phones. We've got these borderless networks. We've got networks now where we can contact anybody, anytime, anywhere. Now, this, folks, I always put on, throw up this, warning. There's some, there's some marketing stuff here because this is a little bit marketing. But at the same time, it is indeed true that our networks are now almost borderless. We take our devices with us everywhere. We can check email everywhere. And again, that's wonderful and it's horrible. It's wonderful because we can do it, and it's horrible because sometimes we have to do it. I get tickled all the time when you see these things on Facebook about, would you go live in this cabin for free if you had everything you needed and no internet for a year? And I'm like, heck yeah, I'm in. Give me a fishing rod and shotgun and we're ready to go. But it is a different world that we live in. Now, this is a switch network, and it is a switch network built on the hierarchical model using core distribution and access layer. There's distribution layers being named a different thing in the data center now, but basically the core layer is your layer that allows you to do high speed, I call it high speed, low drag, redundant connections to the internet. That's your core. Your distribution layer is where you do your security, aggregation, control of traffic. And then your access layer is literally connecting to devices. The beauty of this model is that it is hierarchical, so you can change out individual layers, and individual layers have a function. It's modular in that, let's say we added another building over here. We could just drop in another distribution layer switch, throw in some cables, and have another distribution layer switch with access underneath it. If you build it correctly, it's resilient in that it can survive a single link failure, and many times a multiple link failure. And it can be flexible. Now the problem with the design that they have here, which is this is a true core distribution and access layer, CDA. It's very expensive when you start building out this type of redundancy. Some places have a collapsed core. In other words, there's a core distribution that are combined, the functions are combined into a collapsed core. Then you have your access layer out on the edges. And again, it comes down to cost. It comes down to, can you afford, 2 Nexus 7Ks to go right here in a redundant array? It depends on your environment. It depends on what kind of money your company has and what you're going to do if that link goes down. If you can still do your job when the network's down, well, then you don't have to worry about it having all the redundancy. If you can't, well, then you better have redundancy. When we look here at the access layer, again, that's the network edge. It's where your traffic comes in from the host devices. The distribution layer is where we do our aggregation, layer 2, layer 3 broadcast domains, and sometimes layer 3 routing boundaries if we're doing layer 3 switching. The high availability with this distribution layer so that you have redundant links. And again, that part of that could be the aggregation, doing PageP or LACP, doing a LACP port channel and having multiple links. So if one goes down, you don't lose entire connectivity. And then you can do classes of service and quality of service using the access layer to define it, and then maintaining that through the distribution into the core layer. In the core, like I said, I just call that high speed, low drag. You try to do it as fast as you can, and you try to make it where the core does not have to do a great deal of the security policy and information. Now, having said that, it still does. A lot of it does, especially in this type of design where it's a collapsed core. So, the role of switch networks. What do switches do? Well, they are designed to filter by MAC addresses. In Introduction to Networks, you learned all about how a switch works with MAC addresses. Basically, switches build tables of MAC addresses, and then they can literally move traffic between only the 2 ports that are talking to one another. Now, that's basically access layer switches. When you get into the distribution layer switches, you'll see the symbol being used for D3, D4, D1, D2, D3, D4. These switches are distribution switches, and they have routing capabilities. They're going to be layer 3 switches. And really all that is a switch that has the ability to also route. Now, when we start looking at what kind of switches we're going to buy, good, I'm glad that fixed it, Jason. The type of switch we're going to buy, well, it always, well, not always, but 99% of the time it comes down to, in part, cost. It comes down to how fast you need the port speeds to be. How many ports do you need? Do you need power over Ethernet to power IP phones and access points and surveillance cameras and those types of things? How reliable do you need the switches to be? Do you need a switch that has redundant power supplies in it so you can survive a single switch power supply dying? Again, frame buffers. What is the backplane speed of the switch? And then scalability. And when we start looking at things like this, these fixed configuration switches, these are the lowest end options. although there are some fixed configuration switches that do have the ability to do redundant power supplies, RPS. But fixed configuration switches typically are access layer switches because we know how many ports we have in this building or in this room, and we have a switch dedicated to that. We may have modular switches like these, and these are chassis that accept line cards. For years and years and years, it was the Cisco 6800 series, that 6500, excuse me, 6509, 60, and now they're 68s. So they're all different types. There's 4Ks that Nexus 4Ks that go into the data centers and the other items. But these modular switches, they're great in that you can put the blade in that you need. They usually have, you see down here, they have redundant power supplies. You have all different types of things available using the blades. The negative is these chassis are very expensive. The blades for these chassis are very expensive. It's one of those things where it comes down to what does your network really need. And then this is something that's called, this is StackWise. This is one of the things that Cisco has come up with. And you can buy switches that are stackable, and then you can use StackWise cables. You'll notice here, if you look at it, this is the here to here to here, and you end up with almost what I would call, what looks a lot like our old school multi-station access units for token ring, showing my age here. But you know, these allow this set of switches to appear as a single switch backbone. If you've ever worked with a Nexus 5Ks, I've only worked with a 5548, but it reminds me of the FEX configuration where you take a FEX and it becomes almost an extension of the 5548. This is even, it's very similar, but this is taking multiple switches that would have been individual switches and then stacking them together. The beauty of this is, depending on how many you need, you can add more to them. You also have the ability that if a single switch fails, you can have recovery. This really is if you can't afford a modular switch. If you need StackWise or stacking technologies, you're really better off probably trying to buy a modular switch. Yeah, loop daisy. Yeah, it does like a loop daisy chain. It sure does. Like I said, it looks like you've got this whole, you've got a loop, so it's kind of wild. I've only seen a couple of these out in the wild. Has either of you seen them? No, I hadn't seen it. Most people, if they're going to do that, they're going to buy, you know, a modular switch. Here we have general switch concepts. So here we have ingress and egress ports. So the ingress port is the port that traffic comes in on, and we see here if it comes in on a port. If the port doesn't already know about well, here's one of the first things I want to tell you that they don't put in here that you should know, is when a frame, because remember, switches are layer 2 devices, when a frame comes in, and the first thing that's going to happen is the port is going to look to see if the source address, well, actually it's going to look at the destination address first. If the destination address is in the table, it's going to look at it, okay, and it will then forward it to that port. We'll also look at the source address, and if the source address is not in the frame MAC address table, okay, or the CAM, Content Addressable Memory table, it will then put that in. So in this case, it's got it and knows where it's supposed to go, and it sends it over and sends it out port 4. So it ingressed in on 1 and egressed on 4. Here we have ingress on 5 and egress on 1. Okay. But remember, by default, when a switch boots up, there are no known destination MAC addresses or well, destination MAC addresses at all in the content addressable memory table or the MAC address table. Now the switch has to build that table looking at the source address of frames that come in on individual ports. Another key concept is in most modern networks, we want to have what's called a full micro-segmented network or fully segmented, and that would be each individual port is connected to a single host and only a single host. And that's how this does it. And there's a little video on how that MAC address table is populated, and you can watch that. Now, some of the things that you need to learn are some of the methods for switches used to forward traffic. One is called store and forward, which is the most reliable in terms of it will not ever send a damaged frame, but it takes the frame, brings the entire frame in, runs a CRC against it, and the CRC is a mathematical calculation to see if the frame's been damaged or changed. If the frame is good, then it will be sent out. If not, then the frame would be discarded. And of course, it doesn't happen when the NIC, when the NIC sends out an ARP request, it would automatically see the source, MAC address, and would place that into the MAC address table. So that's how it learns it, from the incoming source MAC addresses. Now, the good thing about store and forward is it's never going to send out a frame that has actually been damaged. The negative is you have to have bigger buffers, and it takes much more processing power on the switch to use store and forward. Now, another method called cut through only takes in a portion of the frame, and then once that portion is brought in this case the destination MAC address, once it receives the destination MAC address, it will then immediately start forwarding the frame out the egress port. Now, the way this works is technically if you get into the part of the frame that has the destination MAC address, there shouldn't be a collision, because a collision should be a runt, which is less than 64 bytes. And so using cut through is supposed to be, especially on a modern network with no errors, should be fast, and you really shouldn't have a problem. You should not be sending out frames that have been damaged. So here we see store and forward again, bring in the entire frame and then send it out after checking the checksum. And cut through, it goes through, and as soon as the entire MAC address is brought in, okay, destination MAC address and the preamble, then it starts forwarding it. So it's very fast. First 14 bytes, and boom, off it goes. Now, that's cut through is one method, and that's actually called fast forward. There's also another method called fragment free. So when I say cut through, sometimes you'll hear cut through being called fast forward or rapid frame forwarding. Fragment free is another type of cut through that brings in the first 64 bytes and then sends it forward. The method used on a switch depends on the type of switch and the level of switch or what it can support. So again, I warn you and I tell you about things. Let's see. There's one page on store and forward. There are switch master methods. There's another, and there's another, and then there's an activity. When I see something 3 times in the curriculum, that gives me a very clear indication that you will have a possible chance of seeing that somewhere in the future. All right, good question. So does cut through even look at the CRC? It does not look at it on the switch. What it would do is it would send it when it gets to the destination device, the destination host. The destination host still runs the CRC to see if it's been damaged in transit. So with cut through, it is possible that the switch could actually send a frame that had been damaged in some way or modified in some way and would be rejected by the host that received it. So it just doesn't run the CRC. Does that make sense? Yep, no problem. It relies on the host. If it's using cut through, it relies on the host to do the error checking. That's it. No error checking on the frames performed by the switch before it's released out of port. That would be cut through. Yay. Trying to get them all right, but you know. Receives the full frame, checks frame for errors for releasing it. Great method to conserve bandwidth on your network. That would be, should be that one. That one? That should be that one. And there. Boom. And the reason this says a great method to conserve bandwidth on your network, store and forward would never forward a frame that is actually damaged. So you wouldn't have to have retransmissions. So if the switch can support store and forward, it's a wonderful switching method. If it can't, well, then obviously you got to go with something different. Now, this is a really cool activity that I like a great deal. And it's an awesome way for your students to learn to understand how switches work. And this is, you've got a frame, destination MAC address is 0F, source MAC is 0B, and here's the MAC address table. And it says, where will the switch forward this frame? So we're going to look and say it's coming in on FA03 from 0B. It's going to 0F, which is over here. All right. So where is it going to get forwarded? It's going to get forwarded out FA9. All right. When the switch forwards the frame, which statements are true? Switch adds the source MAC address to the MAC table. Well, let's look. FA3. No, it's already in the MAC address table, so that's not true. Okay. Frame is a broadcast frame. No, it's not, because the destination is not all F's, so it's not at all. Frame is a unicast frame, will be sent to the specific port only. That is true, because it is a frame destined for 0F, which is on port FA9. Frame is a unicast frame, will be flooded to all ports. That can never be true, because unicasts are not flooded. Well, okay, I won't say it can never be true, because if you have, there are some security tools out there that you can overwhelm the switch MAC address table, and then it would forward a unicast frame out all ports. It just doesn't normally happen. And the frame is a unicast frame would be dropped at the switch. No. Correct. So we got it right. Then we can go to a new problem, and it goes on and continues on and gives us new problems, new problem, new problem. And so your students can use this, and you can use this to look at how the switch is going to react. For instance, here's another good one. Let's do this. 0A is destination, 0F is the source. Where will the switch forward the frame? Now this one's interesting, because you look at it and you go, well, the destination is 0A. If the destination is not in the MAC address table, what does the switch do with it, for that frame? It's going to forward it out all connected ports. So we'll actually send it to FA1, FA3, FA5, FA7. It will not send it to FA9 because that's the port it came in on. Okay? And it says this, the switch for the frame, which statements are true. Switch adds the source MAC to the MAC table. Well, no, because 0F is already in the MAC table. It's a broadcast frame. No, that's not true, because it's got a destination MAC, 0A. It's a unicast frame we sent to specific port only. That's not true, because that port is not in the MAC address table yet. It's going to be flooded to all ports because of that. And the unicast frame is dropped to the switch. No. So now we go check. And there's another example where a unicast frame would be flooded to all ports. That's only going to happen if it's not in the MAC address table already. Okay. So really good activity here, your students, and you can go through to learn how switches work. By the way, I was once asked at a convention, hey, what is a switch? And there's all these people giving definitions and everything. I was like, it's a multicast bridge. Because in the old days, okay, and unfortunately, again, I was going to have my Surface tablet up and running so I could draw. But in the old days, we had bridges, and bridges are just two-port switches. That's all they are. So all a switch is a multi-port bridge. Now, what are collision domains? One that always broadcasts the 0E. 0E, no, it would only broadcast FF, because once at 0A, 0E, oh yeah, 0E would have seen that too. Yes, the hub would have sent it over. In that last example we had where 0F was sending to 0A, that would have gone up to the hub, it would have come down to 0E, and then it would have went up to FA9, yeah. Just remember what I say, hubs are of the devil. The only place you really should be using the hub is if you're trying to sniff traffic for some reason. I really don't even like them putting hubs into these diagrams, but you know, they do. Hub is just a physical air device that in many cases repeats the signal. But I say hubs are of the devil. Now, what is a collision domain? A collision domain is any area within which collisions can occur. On a modern switch running full duplex, you should never have a collision, period. If you are having collisions on a modern switch network, you've got problems. Now, what is a broadcast domain? It is the area within which devices must deal with or look at or process broadcasts. Now, remember, when a frame comes in destined for, I say that like a cat because it's the all F's MAC address. When that comes in, the switch, that's never going to be in the switch MAC address table. So any broadcast will get forwarded out every port except for the port it came in on. That's why broadcast storms are so bad in a switch network. That's why I also tell people that broadcasts are bad. You can't avoid them totally, but they are bad on networks. So we see an example of a single broadcast. The more switches you connect, the bigger your broadcast domains are. What breaks broadcast domains? What have we already talked about that breaks broadcast domains? Excuse me. Routers, exactly. Routers are layer 3 devices, and they stop broadcast domains, or they create broadcast domains. So switches can alleviate congestion because we've got the ability to have high port densities, high speeds, large frame buffers, fast internal switching. Really, most modern networks today will be micro-segmented, and that was actually the term I was looking for a while ago, and it's a single port for all of them. So now this is a little tough for me on the computer, but this says draw the broadcast domain. Okay. Correct. That whole thing was a broadcast domain because those are all evil hubs. Now this, again, would be all of these down here, and again, this is not very easy to do with and it's going to tell me I'm incorrect because I can't draw. There. Now see what it's doing here is it's actually, and this is where it's aggravating with this activity, it's actually wanting you to grab the port on the router and bring it down, which it is part of the broadcast domain. Okay. And there's no difference between those and the one before. Now this is a little different, isn't it? Nope. Not a lick, because it's still one broadcast domain. Because remember, it would be everything. Ooh, that may not catch it. We'll see if it will. Check it. Nope. And so that's where it's a little weird for these. Yes, that won't work. These things are obviously not made for somebody with a spinal cord injury whose hands do not work well. There we go. Got it now. What? Oh, duh, I'm a doofus. It helps if you read each collision domain. Not broadcast domain, collision domain. Remember, every port on a switch is a collision domain. There'd be one there, there'd be one there, and there'd be one there. Boom. Now we got it. Now it's just being mean to me. Okay. That's what it is. This is a collision domain, that's a collision domain, and that's a collision domain. So, and here you can show the answer. There it is. I just can't draw. Well, pretty good. Here we've got collision domains again. Imagine this would be actually 1, 2, 3, 4, 5, 6, 7 collision domains. So collision domain is the area within which collisions could occur. And when you segment a network using switches, your collision domains, there are more collision domains. I might be getting the hang of this thing. Oh, so close. Getting so close. Okay. All right. So, how do we do basic switch configuration? You put a host name on it, just like you do with a router. You put, in fact, we're just going to go through and do this. I'm going to show all, because what you do on a switch is you put a host name, give it enable secret, you give it console and V2I passwords. Now notice here is something different. On our routers, we only had 0 to 5, 0 to 4. Yeah, 5 total. We have 16, 0 to 5. Man, I'm drawing a blank. Here's one of the advantages of having packet tracer. But either way, we had fewer. We didn't have as many 0 to 5. We did not have 16 VTY lines. We had a smaller number. Now we have 16 on a switch. We got to do VTY 0 to 15. It's embarrassing. It was 5. Yep, 0 to 5. It's embarrassing when you forget something like that. It's so simple. There's 0 to line VTY 0 to 5. And then you've got to encrypt your password so no one can do shoulder surfing. You take a VLAN 1 and put an IP address on it, no shutdown, and then you save it. Now, the other thing that they don't show you here, that they should have shown you, okay? Now, first off, I'm going to go ahead and tell you, real world, we're never going to put an IP address on the VLAN 1 interface on a switch because all ports are on VLAN 1, and that is a massive security hole. Number 2, they have not placed a default gateway on this switch. So even though you've got an IP address on it, unless you're in the same physical network as this particular switch, you're not going to be able to get to it. So I always tell people that default config should also have the IP default-gateway command, which is a global command that is available. That's the only thing I really see they missed here. Otherwise, it's 0 to 4, which is 5. Okay, I'll fix my error there. But you will see it's pretty simple. Again, host name. Now we teach this. We teach using VLAN 1, but then we will very quickly jump around and say, hey, hold on, don't really do that in the real world. You need to set it for a management VLAN that is not on VLAN 1, and then take all of your ports out of VLAN 1, shut down unused interfaces, all those types of things. So, folks, that is Chapter 4. And that is looking at basics of switching. I'm going to go ahead and go through in here to 5, and we're going to look at switch configuration. When we look at the boot sequence on a switch, it is just like a router. In other words, your power on self-test. And then after that, the bootloader will go in and will go and look for the iOS and flash. You also can have a command, the boot system command. One of the cool things about the boot system command is you can, on many switches, have multiple iOS images because they have a bigger flash, and you can change, say you want to upgrade from one to another, you can just go in and do a boot system flash : and put in wherever the new iOS is, boot the switch, see if it works. If it doesn't work, then you can get back into a basic ROM monitor mode and do boot system command and have it boot from the other one. But again, post, locate the iOS, load the iOS in memory, and then go from there. No different than a router. Now, recovering from a crash. One of the things you'll see inside of a switch, if you do a dir flash, you'll see the contents of flash. You can see your iOS image if it's in there. The config file is not startup-config like it is on a router. On switches, especially 2960s that we use, it's config.txt. You can also have other items in flash, depending on what it is. But if you do need to access the bootloader and you've got a damaged operating system, you can actually do that by holding the mode button down. You take the power off, put the power back on while holding the mode button down. Hold it for about 15 seconds and then let off. Then it will go into a bootloader, which is switch : That gets you into a base ROM monitor mode that you can use to then troubleshoot your switch. If you delete the iOS off of your switch, it is a pain to get another iOS image in most of the time. So just be aware that's not the most fun day in the neighborhood. Green, good. That's what I tell students. Green, good. Any other thing, bad most of the time. And, you know, it's not always that way, but typically. But you do need to know what your LEDs stand for. For instance, I have a gigabit switch at home. One of the LEDs is amber. You immediately start to freak out, but then you realize, oh, that's connected to a 100 megabit port. That's why it's amber. So you need to know what your LEDs stand for. Obviously, we have the system LED, which should be green if the system's up and running. RPS is redundant power supply, so it happens to be available. Stat, you can hit the mode button, go down to stats, and I'll show you the stats across your ports. Your port duplex mode, and then port speed. All these can be accessed by hitting the mode button. then it changes the link lights across the top so that you can actually see what ports are on what status. This is good if you're having issues, maybe you're having collisions and you're trying to figure out if without going into the command line if a port's working in half duplex. We got a power issue the other day, and it's funny because I come in the office and there's problems and like, well, it's not working, this is not working. I'm like, well, let's go in here and look, and literally leaned over and like, oh, look, there's no green lights. And we had a device die when a UPS died in our closet. So it's one of those things where LEDs, layer 1, it's good to use them. Basic switch management is just like a router. You take your console cable, connect it to a console port, 9600 8N1, and fire up your terminal emulation program. The difference between a switch and a router is we don't put on a switch typically an IP address on a port. Now, it is possible on many switches to use a command called no switchport. When you do that, you end up with a port becoming actually a routable port if the switch supports it. So be aware it is possible on some switches to do that, to create a port that you can place an IP address directly on. It's not something we typically do and not something taught in this part of the course right now. For right now, we take and use a switched virtual interface, which is an SVI that you configure. So you go into the switch, you create an interface, again, interface VLAN 99 in this case, IP address, put it on that, and do no shutdown. You will then have an SVI that you can connect to and use. Then you need to put in your default gateway. Just like I said, this should be a base command. They should have shown you in the last chapter when they were talking about basic commands. An IP default dash gateway and the IP address of the router port on the same network as your switch. This port right here and this port right here, or at least this port here would have to be in VLAN 99 if they wanted to communicate with one another. So again, once you create this SVI, it will not appear as up until it's created and there's a connected switch port that is associated with VLAN 99. So in this case, you'd have to go into this port right here and go interface FA whatever, and then you have to go VLAN name, and then have interface to switch port access VLAN 99 for this port and this port. We'll do a lot more about that. We'll do a lot more as we go forward, but just be aware when you're doing that in the labs, that's why they're having you do that. Basic lab switch configuration, we will do that lab. Duplex, I always use my Discovery Channel examples for this. If you've ever watched Discovery Channel and they're doing a show from Everest, you always say base camp to camp to OVA. It's always British people. But they do that because the OVA, because walkie-talkie is half duplex. It can either send or receive. So they're saying now it's your turn to send while I receive. That's half duplex communication. There's also simplex communication, which is from a central point out only. But what we want is full duplex, where we can send and receive. In other words, transmit on one side is connected to receive on the other, and vice versa. So that ensures we don't have collisions. Now, switch ports can auto sense duplex and speed settings. I will tell you this, I've seen many problems with auto sensing of speed and duplex settings. So if you can, you should hard set your ports to be the speed and duplex you wish them to be. So you go into the port itself and you say, I want it to be duplex full, speed 100, speed 1000, whatever it happens to be. On our 5548, using non-Cisco SFPs, I have to actually hard set the speed and duplex, otherwise it will not even recognize the SFPs on those particular ports. So this is something that you will use with lower level switches all the way up to high level switches. Again, they just have it shown here. Go in, FA01, duplex full, speed 100. And do a copy run start or use the WR, which is what I use a lot of times because I'm lazy. The other issue we have here is it's called configure auto MDIX, which is auto crossover. By default, if you put two switches connected together, since they are like devices, you should use a crossover table between them. However, with modern switches and modern devices today, most of them will auto cross. In other words, they will realize it's a crossover between two like devices and will do it for you. So you can actually do MDIX auto, and that will do auto cross for you. it's off, then it's a pretty wild way to go see it. But show controllers, Ethernet controller FA015, up, include auto index, and see it on. Not hard to do at all. Going to verify a switch, you can do show interface, FA01, FA0 gigabit, whatever. Show startup config. I don't really consider that to be a verification command, but you can see stuff. If you want to see the file system information, show flash. You want to see what version of iOS you're running and other items about your switch, show version. Show histories of commands just like it was on the router. Show IP brief. You can still do that on a switch and it works well. And show MAC address table to show your MAC address table. So here's your switch config again. You're going to have a host name, VLAN, default gateway, and that's really your some of the big things. And show interfaces, FA018 will show that it's up. It'll show what speed it's running at. Okay. It'll also tell you whether it's full duplex or half duplex. Here we have full duplex running 10 base, 10100 base TX. Also show you whether or not, again, full duplex is on, whether that's running. Okay, so one of the things we'll see here is Ethernet is up. The first item is physical layer. Second item is data link layer. You can never have a down up because you will not have line protocols being up when the layer 1 is down. So up is good. Down obviously there's an interface problem. It could be that you don't have cable in. Could be that you got wrong, an error with your cable. Could be a different problem than that. You can look in the interface, and by the way, if you ever see up, down, that could be a layer 2 issue. You see that more often on routers with encapsulation issues or with PPP authentication issues, those types of things, or any type of authentication issue. If you go to look at an interface, you can actually look at the statistics for it, so how many runts there are, how many giants. If I see a lot of runts, that means I'm having collisions in most cases, or it could be other things, but collisions in a lot of cases. I see a lot of giants. It may be that I got this switch in the data center and my server's running jumbo frames and I forgot to enable jumbo frames on my switch. 2950, 2960s I don't believe support jumbo frames, but I can't be absolutely sure of that. I'll actually go ask the Holy Google, but I don't think they do. But high-level switches will support jumbo frames. Lied to you. I believe it actually might. Yep, it does. 2960s do support jumbo frames. You can change the MTU. Yep, okay. I lied to you. But I rectified my lie. So it does support if you change the system MTU. But be aware if you are running jumbo frames, that's any frame above the standard size of an Ethernet frame, which is between 15, 14, 15, 18 bytes. Here again we see input errors, giants, buffers, CRC, runts. Those again are normally collisions, giants, CRC errors, output errors, collisions, late collisions. Late collisions a lot of times are because you've your cable run is too far, so you're having late collisions. All those can be seen inside of the show interface. And it talks a lot more about some of these in here, output errors, collisions. That's only in half duplex. Late collisions, again, common, one in half duplex, one in full duplex. Really should never have some of those problems like a late collision or any of those things. When you troubleshoot media issues, you do a show interfaces. Is it up? If it is, are there any indications of noise? In other words, are there any errors going on? Verify duplex settings, those types of things on both ends. Problem solved? Yeehaw. If not, then you can escalate it. If the interface is not up, then obviously you go check layer 1 first. Is there? Yeah. You would be amazed the number of times it's simply, oh, I'm plugged in port 6 instead of port 5. Or the speed's wrong, or the port's shut down because, like I said, by default, ports on a switch, they're not in use, should be shut down. So when you add a new item and put it in a port, if you put it in that port and forget to do the no shutdown command, then the port will be administratively down. Oops, sorry. We do not want to telnet to our devices. Telnet is open, so we should be using SSH, and that's what this shows you how to do. And that is, you configure SSH, and you need to know this, but you set your domain name, you generate a crypto key generate RSA to generate a public-private key pair, create a username, you have a secret password, and you go line V2I 0 to 15, which is your V2I or terminal access lines. Transport input SSH, and that will allow you to SSH from a device over to your switch, and then do login local. And I would also change the SSH version too, so that you're more secure version of SSH. And then you will be able to do that. And you can see this is just an example of doing that for you. Verify SSH. You can open up PuTTY or any Super PuTTY, whatever you use, and you will PuTTY or SSH, not PuTTY, you'll SSH to your switch IP address, and then it will prompt you for username and password, and then you'll be logged in your switch. With PuTTY, all of your with SSH, all of your communications will be encrypted, so you don't have to worry about anybody eavesdropping and snooping on you. Folks, that's where I'm going to stop. I'm going to stop right there on port security, right for port security. And I'm going to stop the recording.